Hello again, astronauts! Welcome to Bad Astra, a wacky science channel where we learn about physics with more costume changes than math. On Wednesdays, we release videos ranging from the Bad Answers series, where we answer viewer-submitted questions, to interviews with scientists about their research, to science-related music videos when we're feeling extra ambitious. Our main content comes once a month in the form of deep dives on scientific topics, from the life cycle of stars, to vaccines, to the history of the universe. Please remember to like, comment, subscribe, share, and check out our Patreon for early access to videos and exclusive content. Shubham Oval asked, what the f*** is momentum? Momentum is the quantity of motion of a moving body. In Newtonian mechanics, it's measured as a product of its mass and velocity. That is, how big the object is times how fast it's going relative to your reference frame. The more momentum something has, the more you want to get out of its way. A speeding train heading towards you? That's a lot of momentum and a good reason to GTFO. A speeding train heading away from you? Probably nothing to worry about because it's got negative momentum. A puppy walking up to you? Not very much momentum, so you can probably stop and say hi. A puppy sprinting toward you? You will experience a collision, but the pain will be worth it. A parked car? Zero momentum. Feel free to walk by. Cars driving on the road? Maybe look both ways before you cross. Momentum is also always conserved. So when there's a collision, like a ball bouncing off the ground, the immediate change in the ball's momentum from reversing direction is balanced out by the ground's change in momentum. Since the ground is a lot bigger than the ball, it has a much bigger mass, and the velocity change can be unnoticeably small. But say a speeding car rear-ends a parked car, and the two cars get stuck together. The new megacar will have the same momentum as the combination of the previous two cars' momentum. Since the parked car's original momentum was zero, it's just the momentum of the original speeding car now spread across two bodies. Since the new megacar has roughly double the mass of the original speeding car, assuming the cars were the same size, the velocity of the megacar after the collision will be about half of the original car's velocity. In real life, friction, air resistance, other cars, etc. would affect the resulting collision, but we're physicists, we can ignore real life. And likely the cars won't even get stuck together. Rather, the speeding car might transfer all of its momentum to the parked car, and the parked car might now be the one speeding. No matter what, it's going to be very expensive for everyone involved, and people inside the cars might get hurt, so I recommend experimenting with little carts on wheels in a physics class instead. Now, in cases with really fast-moving objects, like objects moving close to the speed of light, special relativity gets involved. Instead of mass times velocity, the equation becomes gamma times mass times velocity. This gamma, or the Lorentz factor, is equal to 1 divided by the square root of 1 minus the velocity squared over the speed of light squared. This gamma has technically always been there, but at low speeds it basically equals 1, since 1 minus 0.0000 whatever is basically 1, so we can ignore it. To learn more about the Lorentz factor and how it affects the momentum of a super fast or relativistic object, check out our video on special relativity. But what about particles without mass, like photons? Do they have momentum? Yes, but the mass is zero, so time to call quantum mechanics. I know, it's the messy drunk friend, but it deals with super small stuff, so it has jurisdiction over photons. Anyways, the momentum of a photon is determined by its wavelength. Specifically, Momentum of a photon equals Planck's constant, a super tiny number, over the wavelength. Also usually a tiny number, but less so. From this, we know two things. One, a photon's momentum is tiny, which makes sense because photons are tiny. Two, the shorter a photon's wavelength, the more momentum it has. This makes sense because shorter wavelengths of light, like ultraviolet or gamma rays, have more energy and are more likely to cause damage than longer wavelengths like infrared or radio. Gamma radiation can damage your DNA and increase your risk of cancer. It can also be part of cancer treatment, but that's squishy physics, so we're not going to get into it. Radio waves, not so much. Although in very high doses, radio waves can still burn you, so science, Tommy, please just don't. Astra out.
Ad Astra, to the stars, to the stars.